Hi guys, my name is Damian Rusinek. I'm a security researcher and a pen tester, and I'm mainly focused on blockchain technology and smart contracts. And last year at OWASP AppSec Europe in London, I gave a talk about the vulnerabilities in smart contracts, and I did a small showcase. But this year I wanted to focus on the whole process of development of smart contracts and show you how to make it, secure. And well, the first question to you: who of you have ever created, implemented, or maybe used decentralized applications or smart contracts? Raise your hand. Just a few people, and I must tell you that this topic is going to be hot quite soon, because these are some of the companies, just a small list of the companies that create platforms for smart contracts and decentralized applications, or just use them. And for example, Facebook Libra. Have you heard about Facebook Libra, the cryptocurrency of Facebook? Yes, actually, this is not the cryptocurrency only. It's a smart contract platform. So it is a cryptocurrency, but you can also create smart contracts on Libra. So let's start with a quick introduction, because the topic is not very familiar. So what are the decentralized applications? And I'm going to call them DApps from now. And why are they becoming so important in your future? Well, decentralized applications are like web applications, but they have decentralized storage and governance. So if we are looking for an example of web applications, we can go for Facebook or Reddit. And Steemit is a decentralized version of Reddit, for example. And well, why are they becoming so important? First, there are many projects that have proven its value. Also, the market is quite huge, because there are billions of dollars in cryptocurrencies, of course, on blockchain market. And it is also a great chance for new technologies, for example, for fintechs. And as I mentioned before, there are big players behind the blockchain technology, the smart contracts, and decentralized applications. But what is so special about decentralized applications? Why do we need them? Why can't we stick to the web applications? Well, the main thing is that we gain trustlessness thanks to the blockchain technology, which means that there is no single point of authority. No one person or institution can control the application. Also, it means that no one can actually turn it off permanently. That's because anyone can keep the copy locally of any decentralized applications. So if somebody turns off the application, anyone else can just put it back online. And it's like having a copy of whole Facebooks, including source code and its database on your computer. So that sounds quite nice. Well, what's the difference in the architecture between web applications and the apps? Well, the original idea behind the apps is that they are kept on blockchain. And I mean both the front-end application, which is usually written in JavaScript, and the API, which is the backend of the application, of this decentralized applications, and these are smart contracts. And all of this is kept on blockchain, on decentralized network that no one can modify and no one can control. So also there is a quite popular architecture where the front-end application, so the JavaScript, is kept on a web server, like in web applications. And that's actually okay, because still, you download the code, the JavaScript code, and you can audit it. You can see it. Of course, sometimes it's obfuscated, but there was a great talk about by Louis about how to automatically scan for interesting stuff in JavaScript applications. So this hybrid decentralized architecture is still okay, because the main logic, the business logic, the backend is on blockchain still. So are these applications secure comparing to web applications? Well, first of all, they are undestroyable. like I said, anyone can bring it back to life because they're using blockchain. Then they are cryptographically secure. I'm sure you've seen that two words together many times when you were, reading some descriptions of blockchain applications. So what does it mean? It means that all transactions which represent function calls are digitally signed. Sounds nice. We have non-repudiation, we have authentication. That's cool. And also, anyone can actually verify the code and the current state of the application because it's all public on public blockchain. So it's like you can read the code. But still, we see many either hacks or great submissions on bug bounty platforms for smart contracts and decentralized applications. So again, it's just about our expectations and the reality. So I'm sure that's not going to be a great discovery for you, but what we need a security for decentralized applications the same as we do for web applications. And last couple of months, we've done some pen tests and security audits for companies related to blockchain. And most of them included, of course, web applications that integrate with blockchain. And some of them also included decentralized applications. Mainly the backend of decentralized applications, which are smart contracts. And well, the case of web applications is quite simple nowadays because we have so many great projects, so many great materials and standards that we can use to perform the audit. And let me ask you, if you need to know what are the most common web application vulnerabilities, what would you go for? OWASP what? OWASP top 10, of course, yeah, the first answer. Then, if you need a knowledge base for the common weaknesses that can happen in web applications. SWE, exactly, common weakness enumeration. And last but not least, I guess the most important, where would you go? What would you go for if you need a security checklist, end-to-end list to perform an audit? ASVS, exactly. Application Security Verification Standard. And actually, we can ask the same questions for decentralized applications because this is AppSec, application security. So, what are the most common vulnerabilities for decentralized applications? There is a project which is very similar to OWASP Top 10, which is called DApps Top 10, that enumerates those 10 most popular vulnerabilities. Also, we can look for a knowledge base for the weaknesses that can happen in smart contracts. And here we have a smart contracts weakness classification registry, which is very similar to CVE again. And last, do we have a security checklist that covers whole smart contracts, the whole security of smart contracts? Actually, we couldn't find any. So, well, there are very many publications, materials about the security of smart contracts, but we couldn't find a checklist that you can, just say that this is passed, this is passed, this is passed. Okay, our contract is secure for now at least. So that's why we have created, together with Paweł Kuryłowicz from our company, SCSVS, Smart Contract Security Verification Standard. It has very similar form to ASVS because we like ASVS and we use it every day for web applications. And we also have very similar objectives. We want to create a checklist for developers, for architects, and for security reviewers. And also we want to help to mitigate the common vulnerabilities by design and to help to create secure code, secure smart contracts. So we have created 13 different categories. The last one is a bit different. I'm going to talk about it later. And they have the same form. So they have as ASVS. So they have the security requirements. All of them contain about 100 security requirements. And I'd like to present some of them on example on the base of the SDLC, software development lifecycle, and show you that these requirements cover whole process. And I must say here that there is a disclaimer. This presentation It's not about how to introduce security into your SDLC, because that's a huge topic and there are many approaches for that. I'm just using SDLC as the base for examples. So let's start with analysis. Well, of course, we have some similarities between web applications and DApps. And one of them is a threat modeling, which we should perform actually for any kind of application. So that's why we have added security requirements to AVS that makes sure that you first define the boundaries, the trust boundaries in the documentation, and that you perform threat modeling for each functionality that you introduce into smart contracts. What about the differences? Well, the first difference is about the sensitive data. Actually, this is quite easy for web applications because we can keep sensitive data in a database and we can just protect it. Of course, this is not very easy sometimes, but still the main idea is to keep it in database that is protected. In case of decentralized applications, it's not that easy because all data is on public blockchain. So actually everything is readable and publicly accessible. So that's why you must make sure that no confidential data is kept in smart contracts, in the storage of smart contracts, and like, for example, passwords or personal data. And no data is considered safe or private, even if you use a private keyword for your storage variables. This is quite tricky because private variables are not that private. The next thing, public access. For web applications, it's quite easy to define what is public. We usually publish the front-end application and some API. In case of decentralized applications, actually everything is public. So each function that is in the smart contract can be called, can be executed. Of course, the logic may be different. The logic may say that, sorry, you cannot execute this function. But anyone can try to execute all functions in smart contracts. And that was the case of the first Parity Wallet hack, where a function that inits the smart contract was publicly accessible. And actually, somebody could took over your wallet. And that's how $30 million of dollars, this is variable, right? So today it's 30 million, tomorrow it's 20, and the day after tomorrow it's 40. So I need to, update this slide every time I give a talk. So for today, it's about $30 million, of course, in cryptocurrencies. So it's important to make sure that all functions have the visibility specified. That this was the case of attack just because the function has not specified the visibility type. And by default, functions are public. So that was the problem. Next thing, randomness. Well, in web applications, it's a matter of for one function call. Either you want statistical randomness or cryptographical randomness. In case of decentralized applications, it's a bit tricky because smart contracts are executed on many nodes simultaneously. So, and they must be executed the same way. So you cannot use any local parameters from one node. And the problem here is that it's not that easy, it's not that trivial to get a random number in smart contracts. And that was the case of actually many attacks, many hacks. One is quite recent from September, where about $100,000 were stolen from EOS Play application. And one is a bit older, where about $80,000 were stolen from Smart Lottery hack. And all that was available because the bad randomness implementation. So you could quite easily predict the so-called random number. So the solution for that problem is to make sure that you do not generate pseudo-random number trivially basing on the publicly available data that is kept on blockchain, like timestamps or block number, etc. Also, decentralized applications introduce some new threats, like threat actors, like, for example, miners and validators. These are the nodes that validate the transactions and add new blocks to the blockchain. And they are quite powerful because they can see the transactions before they are validated. So they know the future. And here is a case of a report for Augur platform where a miner could easily abuse the business logic of this contract. So he could easily DOS the contract just because some of the logic was based on variables that can be set by miner. And that's how and as you can see, the severity of this vulnerability is high. So that's important. So to solve this problem, we should make sure that the contract logic implementation corresponds strictly to the documentation, and also that we have business limits and we enforce them. And by the way, we must make sure that our business logic does not disincentive users from using our smart contracts, because if using our application is too expensive for users, they will stop using it. It's actually also some kind of denial of service, right? Okay, so let's move on to design phase. We have some similarities here as well. One of them is the least privilege rule, and the other is access control, which actually in case of decentralized applications is a bit tricky because it's, again, public, so anyone can see the rules. And that's why it should be kept as simple as possible and centralized in one smart contract. And the least privilege rule can be ensured with the requirement that makes sure the creator of the contract does not have too much power. Because, when you create a contract, when you implement it and then you deploy it, you can say that, okay, I'm the owner, I can do anything. But then you lose the trustlessness, right? Because people have to trust the creator of the contract. So the best approach is to create a contract that cover all the business logic flows and that creator cannot change, because then it's really trustless. And also the access control mechanism should be kept in one smart contract and which is trusted and should be, as I said, as simple as possible. Next difference are loops, and I mean the loops that lead to denial of service. Well, we have that kind of loops in web applications. They are usually infinite loops, but it's quite easy to find a loop that potentially may be infinite. In case of decentralized applications, we have some loops that are not infinite, but they are so-called unbound. So there is no specified exact number of iterations. And if we have such loop, we can have a problem because, as an example of governmental smart contract, the array that was looped became so huge because of some kind of business logic. It became so huge that actually you couldn't iterate over it. And that was the requirement of the business logic. So you had to iterate over an array and that would take so much, that would be so costful. It would take so much gas, even more gas than the maximum allowed number. So you actually couldn't call it anyway, because you cannot give so much gas. It's more than maximum allowed number. So that's the story how about $200,000 were frozen. It means that they are there, they are on this contract, but you actually cannot do anything with that. So to solve that problem, you can first of all, do not iterate over in unbound loops. You must specify exact iterations for each loop. And also to avoid other problems with gas limitation, you should not send funds, I mean the cryptocurrencies, tokens automatically in your business logic, but you should store the number attached to a person, to an address, and allow those people to withdraw their tokens or cryptocurrencies with another transaction, with withdrawal transaction. And also, we have another case of the risk for decentralized applications, because as you've seen, on most of the applications and smart contracts, there are some cryptocurrencies kept. So the more cryptocurrency is on the smart contract, the bigger the risk is that somebody will try to steal it. So you can try to decrease the risk, and you should keep as less amount of cryptocurrencies on the smart contract as possible, because that just disincentives the hacker to steal your cryptocurrency. Okay, so let's move on to implementation. Of course, we have great tools like Truffle or Remix. These are IDEs, and they actually perform some security, basic security checks. That you can integrate some other platforms that perform some other security checks. But so it's like partially covered. The security is partially covered by these tools, but still we have so many bugs, and it's very similar to web applications, right? So one of the most common vulnerabilities in smart contracts are arithmetic bugs. They are not that common in web applications now. Maybe they are a bit more common in the software that web applications use, like servers, where we have overflows. But they are quite common in decentralized applications. And I'm not talking about simple overflows, like, adding two numbers and we, get the number over the maximum. I mean, a bit more sophisticated overflows, where, like, for example, batch overflow or proxy overflow, and details you can find under these links. But actually, there is a quite interesting consequence of overflows, because if we take an ERC20 smart contract as an example, which is a contract for managing a token, which has some value in fiat currencies like dollars, you can actually, using this vulnerability, create decillions or even more of tokens. So it's like going to the mint in real life, printing like millions of euros and going out with legal money. And if you've seen La Casa de Papel or Money Heist in English, if you've seen this series, I'm sure that you know the scenario of this attack. So to avoid such problem, well, you should make sure that you are not vulnerable to arithmetic overflows, and you can achieve that using, for example, SafeMath library. You should also consider extreme values in your business logic and, handle them. And also, sometimes strict equalities are a bit tricky, so you should avoid strict inequalities, sorry. Okay, another difference, recursive calls. Well, recursive calls are quite explicit in web applications, because we either need a loop or we need to call a function inside the same function. In case of decentralized applications, you actually don't need a loop, or you don't need a function call in a function to obtain recursive call. That's because you can call one contract you can call the other contract from the original contract, and the other contract will call again your original contract. So we have a loop, but between contracts, not in the business logic of one contract. And that was the case of, I think, the most known attack in the smart contracts world, the DAO hack, where about 3.6 million ethers were stolen, which is like now, I guess, billions in dollars. And actually, that was the case why the Ethereum platform forked. And now we have two cryptocurrencies, Ethereum and Ethereum Classic. So that was a huge thing. You can find some more details under this link. So, and even this kind of attack got its name. It's called reentrancy. So if you want to avoid reentrancy attack, you must make sure that no recursive calls from untrusted smart contracts are available in your smart contract. And also you should check the result of function calls for low-level function like send, call, because these functions does not bubble up the exceptions. Because these functions, when they fail, they just return, for example, 0, like in C language, right? So you should check the result, because if you do not, and you assume that it always success, then you might have a problem. Okay, testing. Well, we have also a bunch of great tools for testing for both web applications, and there is plenty of automatic scanners for decentralized applications. And we recommend to use them, because why not? You have them and you can easily just run them. So that's why we have added the requirement to use these automatic tools. And we've also created a whole category just to make sure that the testing takes place in the whole process of the development, right from the analysis to the implementation and deployment. And that's why you should verify the contract logic. You should use the automatic scanners. You should also formally verify the specification of the smart contract even before you start to implement it. Right after you design it, you should formally verify it. And also, you should not forget about the manual tests, because some kind of bugs, security vulnerabilities are hard to find by automatic scanners. And that's actually the same like in web applications. And that's why we recommend to provide SCSVS, of course, and other security requirements and policies to all developers and testers. And talking back about the vulnerabilities that are hard to find, we can talk about another submission. This time it's for MakerDAO platform, and it's again on Bug Bounty platform, HackerOne, where a vulnerability which was in the business logic, so it's hard. It's actually it cannot be found. It cannot be found by automatic scanners. It allowed to mint DAI, which is cryptocurrency in this platform, without cover. So it's like, again, minting new money, like printing dollars without, authority. And as you can see, this bounty is quite huge, and it means that this is also a huge problem. The severity is high. So first, what you should do is to make sure that your business logic is consistent, and that, of course, it's proceeded in the sequential order. This check is actually very similar to the check from ASVS about the business logic in web applications. Okay, so let's deploy our application. We have implemented it. Now we want to deploy it. And usually deployment means like setting up some configurations, some integrations, and publishing the application. And usually for web applications, we do it once. Of course, we can later redeploy it, but deployment is the process that we perform once. And then there is no logic in the source code of web application that performs the deployment. In case of decentralized applications, you must perform the same process. You must do some configure your smart contract, and then set up some connections between contracts, and then execute a function that deploys your contract. But the difference is that the deployment function is in the contract. So it's still on the blockchain. It's accessible, so you can try to call it again. And what if, let's say, you forgot to call this function, so you actually didn't initialize the contract? Or what if you allow to reinitialize your contract because you thought, well, I initialized it, and I forgot actually to stop other people from initializing it again and taking it over. So that was the case of the second parity wallet hack, where there was a smart contract that was shared by hundreds of other contracts, and this contract was not initialized. Some guy found out that he can actually initialize this contract. And by initializing this contract, I mean, he took over this contract. So he became something like owner of this contract, and he could execute some sensitive functionalities. And one of those functionalities was self-destruct. So firstly, he took over, he initialized the contract, he took over it, and then he killed it, like removed it from the blockchain. And the problem was that all other contracts were relying on this contract. And when there is no more the core contract, they could not operate. And the other problem was that there were about 500,000 ethers on this, which is about today $100 million. And again, these ethers are frozen actually at the moment. So they are there, but nobody can touch them. So, it's nice to have good money, but if you cannot use it, if you cannot spend it, it's not very nice. So, to avoid such situation, the solution for that problem is making sure that all your variables are initialized, which means that basically your smart contract was initialized during deployment, and making sure that you cannot reinitialize, so you cannot call again the initialization function. And by the way, in this case, there was that sensitive functionality, self-destruct functionality. So you should make sure that you really need such functionalities in your smart contract. That contract did not need self-destruct functionality. Okay, maintenance. Well, when we maintain an application, we of course get some logs. And in case of web apps, we keep them safe on the server. Nobody can read them but the administrators. In case of decentralized applications, it's actually, we also have logs. They are called events. And the difference is that they are published to the public blockchain. So actually, it's like you have logs, but all other people also have your logs. And that's why you shouldn't, of course, put some sensitive data in these logs, but you should monitor them. Because in blockchain, when you find a vulnerability, it's always a race. Who's first? The owner of the contract that tries to fix the vulnerability, or the hackers? So you should make sure that you respond, you have that incident response, in this case, event response, in your applications. And actually, these can be some kind of microservices that are running on centralized servers. They don't have to be on the blockchain. And talking about the security alert and fixing the security bugs. Well, in case of web applications, you can, this is the general concept. I know that it's not that easy always, but you can take down your application, patch it, like deploy the fix, and then redeploy it, turn it on again. In case of decentralized applications, it's not that easy, because once you deploy the smart contract, you cannot just simply take it down. But the bug needs to be fixed. So the idea here is to, and this, of course, this is arguable, but the idea is that you should fix the bug and then redeploy your whole, actually deploy again all your smart contracts. And to avoid such problems, you should first have a functionality, some kind of mechanism that will allow you to stop the most sensitive functionalities in your smart contracts for some time. However, this mechanism cannot, it must still be able for people to access their assets, like, for example, tokens. If your smart contract platform has some tokens, uses tokens, you must allow the owners of these tokens to transfer it or to withdraw it, whatever. So only the functionality, the business logic should be stopped. And also you should make sure that there is an upgrade process for the contract, which allows you to deploy the contract again. Of course, there is no one great solution for that. There is no one upgrade process that solves all problems. This is individual, but for each smart contract platform, you should think over such process. So to sum up, SCSVS is well, we can say that it fills the gap of the ASVS in the decentralized applications world. And I told you that we have that one known attacks category, number 13, which is actually a category that allows you to quickly check whether your smart contract is vulnerable to well-known attacks in the decentralized world, of course. And actually, these are the requirements that are references to other requirements from other categories. So, for example, if you want to check whether you are vulnerable to silent falling sends and unchecked sends attacks, you just need to pass 4.6 and 4.7 requirements. So these are the requirements from the category number 4. And if you want to make sure that you are not vulnerable to reentrancy attacks, you should make sure that you pass 4.5. Okay, so the next plan, the future plan about the SCSVS is to publish it open source on GitHub, on our company's GitHub. And we're going to do it on the 1st of October. If you want to be informed about this, you can either leave me a card after the presentation or just sign up under this QR code. And of course, it's only used for SCSVS alert. That's not, there's no any spam from this mailing list. And we are also considering running SCSVS under OWASP. And we would like to build a community around this project. So if you feel invited, if you'd like to contribute to the project when it's on the GitHub published, just, just contribute. Okay, so if you need a security audit, go for SCSVS from the 1st of October. And as I said, if you want to be informed, just leave me your contact. Thank you. Do we have any questions? Mm-hmm.
Just a second.
I want to give mine. Actually, we don't need microphones here. Sorry.
Thank you for your presentation. You have a lot of knowledge about known vulnerabilities now. And I think that a lot of those are part of the Solidity language. Do you also work together with creators of that language?
No, I do not cooperate with them. However, well, it's a bit true because the language is not very secure by design. However, there are other approaches, like, for example, Viper. There is a language for Ethereum, because I was mostly talking about Ethereum platform, which uses Solidity language. But there is also a Viper in Python that translates your code into Solidity, but has some mechanism that gives you more secure code. But also the hack about EOS Play was from EOS platform, which uses a bit modified C++. So they also have problems that arise from the fact that from the C++ language. I think the good approach is with Cardano platform. They use Plutus language, which is based on Haskell, a function language, and that's a good approach in my opinion, because you can easily formally verify such contracts.
Okay.
Anybody else?
But the simple answer is yes. Some of these are just because of the Solidity.
If there are no more questions left, then I would like to say thank you.
Thank you.